the graph of y equals 2 to the x. All right. So we want to look at this graph. What do we know about the graph of this exponential function? Where's it going to cross the y-axis? At 1, 0. And we know that if x is 1, y is 2. And it's going to look something like this, right?
How did you know that it crossed the y-axis at 1, 0?
All exponential functions do, if there's no shift to them, but anything to the 0 power is?
Oh, it's 1.
1.
Got it.
All right. Yes?
Is there a point at 1, 0?
Yes, it crosses the graph at the point 1, or 0, 1. 0, 1. All right. Yes, ma'am? Yes. All right, so here's our graph of our exponential function that has a base of 2. Does this exponential function have an inverse function?
Yes.
Yes, it does. It does have an inverse function because it passes the vertical line test. So if we were going to try to find the inverse function, first of all, we'd have to say y equals 2 to the x.
Is it the vertical or the horizontal?
Did I say vertical? I meant horizontal. Thank you. Then what would we do? If to solve for the inverse function, what would we do after we set y equals to 2 to the x?
Solve for x.
What? No,
Well,
solve.
switch the x and the y.
Then it's already solved for x.
Okay, can we solve that?
No.
Not in this form. All right? Y is in the exponent, so we can't solve it in this form. And that's going to lead us to a definition of a logarithmic function. Or a definition we'll use this year. Next year we'll have a different definition in calculus. But the definition of the log function with base a. So whatever the base is, this definition applies. X has to be positive. A has to be positive, and A cannot be equal to 1. So the definition of the logarithmic function says that y equals the log base A of x if and only if x equals A to the y. So that's a good enough definition for us for this year. Next year we'll look at a little better detailed definition, but it wouldn't make any sense right now. All right, so really, y is an exponent. Those are the same y's. We can rewrite a logarithmic function as an exponential function. So let me move this up again. We can write it in log form or exponential form. We can go back and forth if we want to deal with logarithmic functions. If I have 2 equals log base 3 of 9, that is a logarithmic function. The base is 3. In this case, our x is 9. But if I want to rewrite this as an exponential function, it becomes, the base is 3. 3 squared equals 9. Remember, we said it has to match this form. If we put log base 2 of 8 equals y. If I want to solve for y, the easiest way to do that is to rewrite it in exponential form. 2 to the y equals 8. Now we can solve this one. You did that on your homework a couple of days ago using the one-to-one function. Can I rewrite 8 with a base of 2? What is it?
2 to the third.
2 to the third. So y equals 3. 3. So if I wanted to come back over here, I could say the log base 2 of 8 is 3. Y equals
Do
3.
you have to do, I mean, if you know what 2 to the whatever power equals 8, can you just say that, or do you have to do that?
If you know what it is, you can do it, but sometimes it's easier to rewrite it so that our thinking processes don't get messed up. Molly?
When would you use log in just like an everyday?
You do have some formulas that use logarithmic functions. Let me look. You have some models, monthly payment models. I see some applications on a mortgage. They can use that, the logarithmic function, in calculating mortgage payments. You just, scientific observations sometimes use logarithmic functions.
Okay.
Justin?
So, what is log? Like, what does
It's a logarithm. Logarithm.
That's in.
It's the inverse function of the exponential function. It's just what we call what it's named. It's a logarithm.
So you're basically saying, like when you have the log function, or form.
Evaluate f of x equals log base 2 of x if x is 32. So we can rewrite this as y equals log base 2 of 32. Now you may know immediately what that is, but for most of us it's easier to rewrite the function as an exponential function. I forgot to put my base 2. All right, so this is 2 to the y. We're trying to figure out what y is. Equals 32. But how can I rewrite 32 with the base of 2? It's 2 to the 5th. So what is y? Y is 5. Or if you want to go back and put it in function notation, f of 32 equals 5. Okay, so here we have the log base 3 of x. I want to figure out what is it if x equals 1. So if we're trying to figure that out, we can substitute y. How would you rewrite that exponentially? 3 to the y. Oops. Okay, what's y going to have to be if it equals 1? 0.
But you said that x had to be greater than 0, and it's y.
X has to be greater than 0. Y doesn't.
Oh, okay.
Y doesn't.
So y should be negative?
Yes. Could be. Let's look at f of x equals log base 4 of x for x equals 2. All right, so here we get y equals 1/2. One more. Because somebody'd ask about, can y be negative? Let's try f of x equals log base 10 of x for x equals 1 over 100. Now notice here we did use base 10, and base 10 is called our common log. And if you were using base 10, you don't even have to put a base. It just, if you just see, say the log of x equals 2, you know you're dealing with base 10. So if you saw the log of x equals 2, you could figure out what x is by rewriting this as an exponential function The base is 10, so 10 squared equals x. So what would x be in this case?
100.
100. On your calculator, the log function on your calculator is base 10. So using your calculator, if we have f of x is a log of x, I want you to find f of 10. Use your calculator. That means we're going to have the log of 10, which equals, Katie? 1. Good. Let's find f of 1/3. What'd you get, Peter? Okay, about negative 0.477. Maddie?
I'm a little confused about this. Like, I understand if it's just says the log of something and then base 10 is understood. Oh, so you would just do like...
Plug it in calculator.
Wait,
That's
how would you enter it in?
log
Okay.
1/3. Log is on the, it's under the x squared key.
I thought that it's like, so if you have like f of 1/3, that's what your x is.
That's what your x is, so the log of 1/3.
Like, but if you're writing it in an equation.
Here you get an error on your calculator because when we define logs, we said x has to be greater than 0. Right, so you get an error, that means it does not exist. You can put D and E for does not exist or no solution. All right, now let's think about this one that we just looked at a minute ago. If I have the log of 10, what's the base there? 10, and that equals 1. Notice these matched. So it doesn't matter what your base is. If this is a property of logs, that it doesn't matter what the base is, whether it's the common log or we'll see in a little bit the natural log. Just some basic properties of logs. If we have base A, I'll just start with this one. I don't think your book names it first. But if we have base A and we're taking the log base A of A, if these two match, this is always going to be equal to 1. Okay. A second property, again, it doesn't matter what the base is. It could be 10. It could be the natural log. It could be 5. But if we have the log base A of 1, this is going to be equal to 0 because A to the 0 is always 1. And here we could think of it if we put it, the first one, if we put in exponential form, it's A to the 1 is going to be A. So if you don't remember, you can always think about the exponential form of that log. But if you remember that if the bases are this, if the base and the x are the same, the value is 1. If the x value is 1, the value of the log is 0. Your y is 0. Now we also have a couple more properties that have to do with the fact that a log and an exponential function are inverses of each other. So a third property says that if we have log base A of A to the x, A to the x is the function, log base A of x is the inverse function. If I plug in A to the x into the x, we should get x if these are inverses. You can just remember this, but it's because they're inverse functions.
Wait.
If the bases match, then the value of this is x. For instance, if I had log base 6 6 squared, this would be equal to 2.
Why?
Okay, 6 to the second power equals 6 to the second power. It has to do with the definition of inverse functions. Remember when we talked, let me pause. Okay, because of the definition of inverse functions, we have this property. The other one would be if we have a to the log base a of x, that's going to be equal to x because those are inverse functions. What you look for is matching bases. Notice here the bases match. And then one more property. That says if the log base a of x equals the log base a of y, then x equals y. This again is the one-to-one property. So let's look at a couple of examples real quick. Log base 4 of 1. What does that equal? 0. Log base square root of 7, square root of 7. 1. And if we did log base 12 of 12 to the third, what would that equal? 3. Or 6 times log, raised to the log base 6 of 20. 20. Notice the bases match. So that's just equal to 20. Okay, let's pause for a minute. Here I have the graph of f of x equals 2 to the x that we looked at earlier. Exponential function. What's the domain of an exponential function? Negative infinity to positive infinity. What's the range of an exponential function? 0 to infinity. What's the y-intercept? 0.01. And what's the horizontal asymptote? Horizontal?
Wait.
Yeah, it's 0.
Yeah.
Y equals 0. All right, so if we have inverse functions, the domains and the range change places, don't they? So for an inverse function, what would our domain be? 0 to infinity. The domain and the range switch places. So the range would be, yes. What about our intercept? Where's that going to be?
Oh, 1, 0.
At 0.10. Because the x and the y change places.
And that's for that x-intercept?
It'll be an x-intercept for the inverse function. And then what about any asymptotes? For the original function, for the exponential function, we had a horizontal asymptote. So what kind of asymptote will we have for the inverse function? A vertical asymptote at x equals 0. So the inverse function is going to look like this. And this would be the inverse, which is equal to the log base 2 of x. Notice our vertical, we have a vertical instead of a horizontal asymptote. We cross the x-axis at the point 1, 0. This is an increasing function. So, and it is, the graph of the inverse is reflected across the line y equals x, which we would expect for an inverse function. If we were to fold those two along the lines y equals x, they should coincide with each other. So that's the graph of a logarithmic function. The thing that would change if the base changes is how steep or how quickly or how slowly it rises. But without any kind of a shift, it's going to cross the x-axis at the point 1, 0. Now, we might have some shifts just like we did with the exponential functions. For instance, if f of x is just the log of x, what does that mean my base is? 10. All right. And if g of x is equal to the log of x minus 1, how will g of x differ from the log of x?
It'll be shifted to the right one.
Shifted right 1. All right, so everything would shift over 1, including our vertical asymptote. So instead of here having a vertical asymptote at x equals 0, where will my vertical asymptote be?
X equals 1.
The vertical asymptote now is x equals 1. And where would be my intercept?
0, 1.
That would be, the intercept would be at the point 2, 0. Everything would move over 1. So if I wanted to find the domain, we set whatever is here greater than 0. So our domain is x is greater than 1. That helps us too when we think about where our vertical asymptote is going to be. What if we, again, thinking about f of x equals the log of x, what if I had a function 2 plus the log of x? How would that switch? It would go, everything would move up 2. So my intercept would also be adjusted there. Probably wouldn't ask you to find that new x-intercept. So the same transformations that applied to everything else that we've done apply to logarithmic functions as well. All right, and real quickly, we had the exponential function with base e. If our original function is e to the x, then the inverse function is the natural log of x. For the natural log, your base is e. ln. In fact, I think you have the natural log on your calculator, right under the log. That is the natural log. And we use ln, ln x. That means the natural log, and your base is e. Yes.
The word after f negative 1 and x is that
Natural log of x, ln x.
ln?
Right under the log. All right, so if our function is the natural log of x, if that's my function, find f of 2. What is f of 2? Calculator. You have to use a calculator. You don't know. What's the f of?
7.8. 7.3.
Wait, I got 0.69.
0.693. I don't have a calculator right here, so.
So it's e to the second power.
No.
Oh,
Natural log of 2.
So you just do
So
L into
0.69.
L in 2. So what was it?
0.693147.
Okay, we'll 0.693, 0.6931. What about f of -1? What do you get there? Error y. X has to be greater than 1, so here it does not exist. What about f of (1 plus the square root of 2)? What do you get there?
0.8813.
Okay, 0.881, 0.8814. Everybody getting that on your calculator? I just want to make sure everybody's finding the right keys. Yes, sir.
How does I know the ln and e are different, but how do they relate?
The base of the natural log is e.
So what makes
Same
ln
base.
different than e?
Same base. Exponential function with a base e. The natural exponential function has base e. The natural logarithmic function has base e. They're inverse functions.
Oh, so the ln is just the inverse of e?
Yes.
Okay.
All right, the ln is the inverse of e to the x. So those same properties that we saw a minute ago for the log still apply. The natural log of 1 is 0. And the natural log of e then would be
X.
no. If you got the same base here,
Is it E?
1. Remember, e to the 1 equals e. Here you'd have e to the 0 equals 1 if we wrote it in exponential form.
Wait, so the natural log is just E?
The base is e. Same with the common log, the base is 10. We didn't write it. With the natural log, the base is e. The natural log of e is 1.
This one.
Uh-huh.
Can you write out natural log form or equation? Or
What
is
do
it
you mean?
possible? You said the base is e. So isn't there like an equation?
So it'd be like ln.
F of x equals the natural log of x. That's it.
But wouldn't there be like an understood e?
There's an understood e there. We don't. They don't usually write that e right there because it's understood that that is base e if it's natural log. All right, those properties hold. Your assignment is on page 234. It is 16 to 36 even. 45 to 50, which is a matching. You're matching transformations on a graph. 52 to 74, every fourth. And then 74 to 78 even.